So we're looking at orbits and rocket science today. And again, what we talked about before I hit record was, if the moon is held in place by Earth's gravity, then clearly Earth's gravitational field reaches the International Space Station. So the astronauts are in the Earth's gravitational field. Why are they floating? And we thought about it for a while, and we said they're floating because there's no normal force. They are in free fall. And so the real question we need to ask is, why doesn't the space station crash into the Earth? Here is a little picture. It says, draw a force diagram for mass little m in orbit around mass big M. So big M, let's say, is the Earth. Little m is a satellite. Let's do a free body diagram. What are the forces acting on this? Now, normally I would say get the obvious. Well, yeah, we're in outer space. We've got to be a little more cautious. So let's pause here. What path is little m tracing out? Where must there be a force pointing? So I know there has to be a force there. And I know in my equation that's going to equal Fc. Does Fc show up on my free body diagram? No. Okay. What force is holding Bryce the moon in its orbit? What force is holding the satellite in its orbit? I'm going to label it Fg. This is not little m, little g, because we're not on the Earth. This is going to be Newton's universal law of gravity that works in outer space. It's going to look like this. Gravity is what's pulling us in a circle. That's the orbit equation. In fact, what I'm going to be teaching you, and you can do this right now, underline the word orbit. That's your trigger. If you see the word orbit, we can say, oh, gravity is what's pulling us in a circle. But we cannot, don't write this down, don't write this down. We can't go, because G up there is not 9.8. What we can use is universal gravitation, which was big G, big M, little m, over r squared equals MAC. Oh! I noticed something. What do you notice? The satellite mass is irrelevant. I'm not going to cross it out here. You can if you want to. We're going to cross it out in the first equation that we do. Tomorrow, when we try and calculate, next class, when we calculate how much fuel it takes to put stuff in orbit, there the mass will not cancel because bigger satellites take way more fuel. But once you're in orbit, it's just as easy to keep the International Space Station in orbit, which is the biggest thing we have up there, as it is to keep a little 10 centimeter by 10 centimeter cube satellite in orbit. Getting it there, the M's don't cancel. This is our orbital equation, but don't write that one down. We're going to fine-tune it a little bit. In fact, here's the key idea. What you can underline, what you want to wrap your brain around, is an orbit is circular motion with gravity as the inwards force. Gravity is what's pulling us in a circle. But because we're going cosmic, we have to use the universal gravitation equation. We can't use little m, little g. Example 2, I like example 2, I like example 2, I like example 2. Example 2 says a 10,000 kilogram satellite is orbiting 20,000 kilometers. Ha! Nice try. Cross out the 20,000 kilometers. How do I go from kilometers to meters? Now, you are going to notice in this unit quite a bit, I'm going to give you distances in kilometers because that's how they're done in the industry. So you'll have to do a conversion. How do I go from kilometers to meters? Times by? So, 20,000 kilometers. Is it going to be 2 times 10 to the 7th, I think? Double check me. I got 4 zeros with the 20,000, and when I times by 1,000, I'm just going to add 3 more zeros. Yeah, so let's replace it with 2 times 10 to the 7th meters. And we're going to underline one more word as well. Can you underline the word above? That's going to become important in a second. Above the Earth's surface. Connor H., what does A want me to do? What path is this satellite tracing out? Where must there be a force pointing? What force is pulling us in a circle? Here's your force equation. Gravity is what's pulling me in a circle. In fact, if you wanted to, instead of writing that, Connor, you could go straight to saying big G, big M, little m over r squared equals MAC. And then you could, if you wanted to, with a little smile on your face, cross out the m's. Connor, what's B want me to find? So, which version of A am I going to put in here? Yeah. What else could I have asked? Instead of saying find the orbital speed, I could have said how long will it take the satellite to circle the Earth? We would call that the period, and I would put in the 4 pi squared r over t squared. In fact, there are 3 variables for orbits. There's orbital radius, orbital speed, and orbital period. If I give you any one, you can find the other 2. And now I've just told you at least 2 test questions. You're going to get a question where I'm going to give you one of those 2 and find the other ones. So what did you say I'm going to find? Orbital speed. So I'm going to go like this, Connor, my friend. I'm going to go big G, big M, little m over r squared equals mv squared over r. The little m's will cancel. I did that on the previous line, but often I'll go straight to this line rather than the previous line as I get good at this. So the key to realize, Connor, kids often forget to put the little m. They want to say force equals acceleration. Some of you did that on your test. When we go through it, you're going to see some of you, especially for the 4 pi squared r over t squared one, I saw a lot of people go, oh, Fc equals 4 pi squared r over t squared. No, force doesn't equal acceleration. Force equals mass times acceleration. So make sure you put the mass there. It does cancel. Oh! I noticed something else. One of the r's will cancel. If you look, this r could move to the top, and I'd have r over r squared. So to handle that one, Trevor, I'm going to cross out the squared and the r, but leave the other r where the first r where it was still. Connor, what am I trying to find? Oh, ha! How would I get the v by itself? Square it? I think square root. This is the orbital speed equation. V equals the square root of big G, big M over R. And you'll notice really it's a one-line derivation. I did not put it on your formula sheet on purpose because it's a one-line derivation. Really the trickiest part is the typing. And this is where I'm going to insist all of you try every one of these today on your calculator. What is big G?
6.67.
Don't confuse big G, which is that, with little g, which is gravitational field, which varies from place to place. This never changes. M, what planet are we orbiting? The Earth. If the question doesn't mention a planet, assume it's the Earth. If we're on another planet, I will tell you. On the test, you may end up orbiting planet Duick, because why wouldn't you? In fact, you may notice that it has a radius of pi and a mass of e, because why wouldn't it? Anyways, little aside. So Earth is 5.98 times 10 to the 24th, yes? Divided by, and then pause and look up. This is very important. What goes in for the R is the orbital radius. Now the orbital radius is from the center of the Earth to the satellite. That right there is our orb. They didn't give me the orbital radius. What word did I underline in the original question? They gave me this distance here is 2 times 10 to the 7th meters. I need the distance from the center of the Earth. How can I find that? Emily. Loud and proud, please. So our orb is going to be the altitude plus the radius of the planet. You're going to have to, one of the tricky parts, read the questions carefully. Sometimes they'll give you an altitude and you have to add the radius of the planet in. Sometimes they will give you the radius. If they use the word radius, then they did you a favor and they measured it from the center of the planet. It's just in industry, we usually talk about the altitude. In physics, we'll talk about the radius. But if NASA is telling you about a satellite, they don't tell you its distance from the center of the Earth. They tell you at what altitude it's orbiting. So we're going to have to go like this then. 2 times 10 to the 7th plus 6.38 times 10 to the 6th. You get what? You're going to find typically orbital speeds are in the thousands. If they're in the tens of thousands, you've probably made a mistake. If they're in the hundreds, you've probably made a mistake, unless you're orbiting like at the edge of the solar system where there's almost no gravity. This one, I think you get just a shade under 4,000. You get 3,800 or 3,900. Try it again. Read me the digits. What? 3, 8. So not 800. 3, 8, 9. I'll go 3890. Is that okay? Is that right? Is it 38? Is that right? Rounded off to 3 sig figs properly? Almost 4 kilometers a second. You're hauling. If you didn't get that, one of the things you want to do over the next few days is snag me and I will help you with your calculator. If you didn't bother trying that, you're setting yourself up for a massive mark loss on the test. This is the test that drives me crazy. Time and time again, I'll see kids with all the right numbers and they have the wrong answers. And I go, oh, they were too, and I don't use this word very often, too stupid to do it during class and move along with us and figure out how to type this in. You also just want to get fast at typing because it'll save you time on the test and in your homework. Is that right? Is it 3890? So here's the question. Can you be at rest and be in a stable orbit? No. No. To stay in an orbit, you are correct, Connor. You do have to be moving. We're going to talk about why that's the case in just a second. But really blatantly, so do satellites have kinetic energy? Are satellites moving with an orbital speed? Is this orbital speed a fairly big number? Do satellites then have kinetic energy, the energy of motion? Oh, heck yeah! Where does that energy come from? Rocket fuel. A lot of rocket fuel. This is why it's so expensive to put stuff in orbit. If you look at the old pictures of the Saturn V rockets, the ones that we went to the moon with, if you imagine the rocket in front of you looking this big, all of that is fuel to put that tiny triangle in the top in orbit. It takes a lot of energy to do this. Couple of comments. I said, notice that orbital speed is independent of the mass of the orbiting object. The little m's cancel. I'm going to write this in the box. You can add this to your blue sheet if you really want to. It's deliberately not on your yellow sheet. This idea that orbital speed equals the square root of big G, big M over R orb. And the reason it's not on your formula sheet, it's really a one-line derivation. Gravity is what's pulling me in a circle. Cancel out some stuff and get the V by itself. Zip zap. Earlier, Emily postulated that the reason astronauts float is because they are in free fall. We're going to prove your postulate. Example 3 says, fill in this proof to show that when an object is in orbit, its acceleration is exactly the same as if it was in free fall. So, here's our proof. It says A equals inwards acceleration. You know what? When you're accelerating in a circle, that's V squared over R. But we just got an expression for V in orbit. It's in the box on the previous page. What did we say? Orbital speed was equal to what?
Square root of big G, big M.
You know what? I'm going to be clever. Instead of substituting V equals, I'm going to substitute V squared equals big G, big M over R, and then I can get rid of the square root, and I'm going to stick that in right there. And what I get for the acceleration when you're in orbit is big G, big M, from the V squared over R, there was already an R on the bottom. From the big G, big M over R, there's another R on the bottom. Although, would we write R? What's a better way to write RR? And if you compare our orbital acceleration that we just calculated as big G, big M over R squared, and you compare universal gravitational field from last lesson, which was big G, big M over R squared, you realize, hey, that is the equation for, we are in free fall. That's the acceleration due to gravity. So if they're in free fall, why don't they crash into the Earth? Here's one of the many reasons we got respect for Uncle Isaac, good old Isaac Newton. Here's what he proposed. He said, imagine you had a big mountain on the Earth and a very, very powerful cannon. He said, if you put a lot of gunpowder in the cannon, Connor, here's the answer to your question. If you shot the cannonball with a really big speed, horizontally, it might actually vanish and actually follow the curvature of the Earth before it hit the ground. If you put more gunpowder in, boom, it might actually make it to there. In fact, if you put more gunpowder in, come here, it might almost make it all the way around before hitting. He said, I'll bet you there is a speed, an orbital speed, if you will, that's just perfect so that even though it's constantly falling towards the Earth, you've matched the curvature of the Earth, and so even though it's in free fall, it never gets any closer to the Earth because it's moving sideways just fast enough to miss the Earth at all times. That's an orbit. So here's the picture that we can draw. Here is orbital speed, and it keeps going and going and going and going and going and going. What that means is, by the way, once you're in orbit, you shut your engines off and you coast. You have to get to the right speed. That's why you're burning your engines. The original Star Trek series, the one from the 60s, one of their frequent tropes, one of their frequent cliches, one of their frequent plot devices, the Enterprise would assume standard orbit, and then something would go wrong with their engines and they would be in danger of crashing into the planet. No, you're not. Your engines are turned off if you're in standard orbit. And so when they brought back Star Trek and they went with Star Trek The Next Generation, the writers insisted they would never use that plot device again. No, I'm sorry. If you're in orbit, you've shut the engines off. You don't need your engines to stay in orbit. You need them to get into orbit because you got to hit that right kinetic energy. You got to hit that right orbital speed. Then you shut them off. So what does this mean then? The fact that objects in orbit are in free fall is interesting. It means, first of all, anything in orbit is always falling to the Earth. It just misses the Earth because we give it the right tangent speed to always miss the Earth. This, Emily, explains why astronauts float around in the International Space Station and in the Space Shuttle. It's not because there's no gravity. It's because there's no normal force, because they are in free fall. It's why if you ever watch astronauts in interviews, they will almost always talk about microgravity. If they're being cautious, they'll never say there's no gravity in the ISS. They'll say, well, when we work in microgravity, that's NASA's term for there's no normal force, but there's still obviously a force of gravity up there. You can calculate it pretty easily. The third thing, then, it means that the inhabitants of the International Space Station feel the physical symptoms of falling. And so you throw up your first few days until you get used to it. That's how it works. Oh, and then once you come back to the Earth, you throw up for again, a few days to get used to having an up and a down and having gravity again. Your inner ear and your vestibular system shuts down after about a week when you're in the International Space Station. And then when you come back to the Earth, it's a fairly painful process of getting it going again. Put your pencils down, look up. Let's have a little fun. In a cartoon, the cartoon character kicks the football, but he kicks it the wrong way. It goes over his head backwards. But he kicks it so hard that it circles the Earth and it passes through the uprights from the other end. How fast would that football need to travel? Or, if we want to say it a little more poetically, if we wanted to orbit right at the surface of the Earth, how fast would we need to travel? Okay. I'm going to underline the word orbit. That's my trigger word. Mackenzie, what's A asking me to find? Speed. Are we in orbit? Gravity is what's pulling me in, and then look up for don't write this next bit down. I'm going to think to myself in a circle, but Mackenzie, what did you say they're asking me to find? Well, then I'm going to bring in the speed circular acceleration one, which is v squared over r. Is that okay? Did they need to tell me the mass of the football? Well, that's convenient. Oh, and one of the r's cancels. Mackenzie, how would I get the v by itself? It's almost by itself. Great. This is why I said I didn't give you this equation on your formula sheet. I think it's a fairly reasonable and easy derivation. And there's a nerd factor because it is rocket science. Okay, so if I hear you correctly, and I think I do, you're telling me that the orbital speed of the football is going to be big G, big M over R, where big M is going to be the mass of the Earth. And this time R, since we're orbiting right at the Earth's surface, is just going to be the radius of the Earth. Okay. Uh, 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. Make sure you know where all these numbers are on your formula sheets, because sometimes you'll forget them because you're tired. They're all in that data page. And radius of the Earth, it's 6.38 times 10 to the what? Is it 6? 6.38 times 10 to the what? Is it 6? Thank you. And no squared? What do you get? I think this one you get just under 8,000, if I recall. I didn't do it in my head. It's just I happen to have this one in my back pocket. Just under 8,000? Yes? Yeah. But the closer you are to the planet, the faster you have to go to stay in orbit. Which makes sense, because the gravitational field is stronger there. As you move further and further and further out, you don't need as much rocket fuel to stay out there. The problem is, as you move further and further out, what happens to your height? What happens to the amount of energy you need to use, the amount of fuel you need to burn to get up that high? It gets bigger, and the trade-off, unfortunately, is not even. Well, why don't you just put stuff way out there so it barely had to move, because it costs way more fuel to get it there than to keep it there. So what'd you get for orbital speed? 7, 9, 10? Is that okay, Mackenzie? You get that all right, too? Be honest. Did you try? Okay, so make sure you snag me later on. I'll show you how to make your calculator sing. It's almost always, it's one of 3 or 4 errors. I've seen them all, and we'll get you there. Okay. Brisa, what's B asking me to find? Period. Gravity is what's pulling me in a circle, except which version of A am I going to use here? 4 pi squared r over t squared. This here, today, this lesson, this is what I had in my mind already last year when I started pushing you all to do formula manipulation. I knew this was coming in Physics 12. Can you imagine trying to do this by sticking in numbers? And, oh, God. Because everything that cancels is so much less typing on your calculator here. What are we trying to find? Does the m cancel? Lowercase, sorry, does the little m cancel? Do the r's cancel this time? Be very careful. In this one, I don't think they do, because this r squared would actually move up to there, would it not? because dividing by r squared, timesing on this side. In fact, you're going to get an r cubed. So don't get, r's always cancel. No, the masses should. The r's won't always. It depends on the situation. What are we trying to get by itself? Where is the t right now? Okay, you know what? Let's draw a little arrow. I'm going to move the t squared right to there in my mind. And that's the only work I'm going to show. Now I'm going to try to derive the equation. So there's a t squared there and an equal sign. How are we going to move the big G and the big M over, away from the t squared? What's on the top on the right-hand side? Well, there is a 4. There is a pi squared. There was an r already there, but now I need to move this r squared over. It's going to end up on top, so that's not going to be an r. What's it going to become? R cubed. And then final step, Brisa, t squared. Screw you. And again, did I give you this one on your formula sheet? No, because again, I'm going to argue it's a 2-line derivation. In fact, if you get good, it's a 1-line derivation. Most of you will get there once you practice this a few times. And the tricky part is the typing. I'm again going to insist all of you try typing this in to your calculator. So you're going to get the period is going to be 4 pi squared 6.38 times 10 to the 6th cubed all over 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th. Mackenzie, you want me to walk you through it, or you want to try solo yourself? Oh, no!
I was on a roll, and then you asked me, and then I didn't.
Oh!
And then I told you no, and then I did it. Oh my gosh. So.
Will that irritate you so much that you'll never make that silly mistake again? Good. Here, going from memory, I think you get something around 5,000. 5,000? So if I go to 3 sig figs, I'll go 5,070? What are the units for this, Brisa? Yep. Just out of curiosity, could you divide that by 60? How many minutes would it take you to go around the Earth? So you'd be circling the Earth every 84 minutes. I know because I'm a nerd, the International Space Station orbits the Earth around every 94 minutes. So the higher up you go, the slower you'll travel, and the more time it will take you to go around the Earth, which makes sense because the circle is getting bigger and bigger and bigger as you go further and further out. Okay. Except, of course, this answer is nonsense. Part C says, why is this impossible? And I think I gave you a hint in Part C, didn't I? What was the hint that I wrote in Part C? So why is this no problem on the moon? What are we ignoring here on the Earth that would totally defeat this? Connor B. Air resistance. Is there air on the moon? Is there air on the moon? It's negligible. It's pretty much a vacuum. So on the moon, we could, if we ever do have moon bases, it's been proposed, find the highest mountain on the moon and make your satellites maybe 100 meters higher than that. Instead of kilometers and kilometers and kilometers up, you could have your satellites orbiting just above the surface. Actually, it'd be kind of nice. It'd be easy to service them, because right now, if we want to fix a satellite, to get an astronaut 10,000 kilometers up there, costs a lot of rocket fuel. To get an astronaut 100 meters above the tallest mountain, you could do that on the moon without much effort. And because there's no air resistance, they'd stay there forever. Yeah. Oh, you're missing out? Okay, quick money. So, in this question, I gave you the radius, we knew r, and we found speed and period. I've told you there's 3 variables when it comes to an orbit: speed, period, and radius. Any one, we can find the other 2. I like this question, I like this question, I like this question. This is a nice realistic question. Suppose we're the weather network and we want to build a weather satellite and we want it to orbit the Earth every 300 minutes. Oh, nice try. 18,000 seconds, yeah? Times by 60? By the way, 300 minutes every 5 hours is really what I... Suppose we want a satellite to orbit the Earth every 5 hours. What do we want the orbital radius to be? Okay. Josh, what's this question asking me to find? Are we in orbit? You know what? Let's underline our trigger word just to remind ourselves. How am I going to start out then? If I know I'm in orbit, what am I going to write? Something is what's pulling us in a something. Gravity. And you know what? Instead of FG, do you mind? I'm going to go big G, big M, little m over r squared is what's pulling us in a... So I'm going to write the m. Which circular acceleration am I going to use here? How do I know the 4 pi squared one? Because they gave me the period. Okay. R over t squared. Is that okay? Do the m's cancel? Cool. Do the r's cancel? Not in this one, because the r's are on different levels. Don't do that. What are you trying to find? Oh, let's get the r by itself. I think I'm going to move these r's on the bottom where I don't like them here on the top. And what will I end up with? An r. Okay, so I'm going to go... I'll write the r cubed. I'll put an equal sign, and now I've kind of got my frame of reference. What am I going to do with the 4 pi squared? What's going to stay on the left-hand side where it already was? Yep. And what else? What's the other thing I need to move? Where's it going to end up? Oh. How do I get rid of a cubed? Cube root? Mr. Dewick, you mean that's actually useful? That's not just something they showed us in math just as a little game? We're actually going to have to find our cube root button on our calculator? Oh yeah, we get a whole new function. So, before you go hunting, stop. We're going to carefully write this out. And by the way, you'll notice I'm taking way fewer shortcuts. Let's write out the numbers, and then I will help you find your cube root button. But let's write out the numbers. So R is going to be the cube root. Which root, Mackenzie? Ah, cool. Of 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. And then I guess it's going to be 18,000 squared. All over 4 pi squared. I'll pause the video. If you need my help finding your cube root button, now is the time. Scientific notation, it's 1.48 times 10 to the 7th meters. Cool. And if you didn't get that, again, over the next couple of days, you're going to get good at your calculator. Mr. Dewick, is this why you went on all those calculator? Oh yeah, this is why I went on those rants already starting last year. I knew this was coming down the pipe. I got to be honest, though. Typically, this is not how NASA would express the answer. NASA would not tell the weather network what radius the satellite needs to be at. They would tell the weather network what altitude. Right? Is that what B asked for? Oh, cool. We have just found the orbital radius. There's Earth. There's the satellite's orbit. So we just found this. We want to actually tell the company that if I know the orbital radius from the center of the planet, how can I figure out the altitude above the surface of the planet? Risa? So we're going to write this down once. I guess you can add this to your blue sheet. It's not on your yellow sheet. I'm going to say altitude is equal to R orb minus, and I'll generalize it, Brisa, R planet, Earth, Mars, whatever. Do you all still have that 148 on your calculator? This is, you've also, by the way, probably learned never clear your calculator in physics. You're often going to use the number that was just there. So it's going to be altitude, whatever you have on your calculator, minus the radius of the Earth. What's the altitude? I think you get 8 something something something. I can't remember, but I think, and it might even be 8.7 times 10 to the, is it 8.46? Is that right? So 8.46, or is it 8.47? 8.47 rounded up times 10 to the meters. Just for giggles, divide that by 1,000. How many, because NASA would give them the answer in kilometers. How many kilometers high is this satellite? What is it? About 8,000 kilometers high, is that right? So the International Space Station orbits about 250 kilometers high. This would be significantly higher than that. Okay. Is that all right? What does C want us to find? Okay. We would use, so let's try that again, Mr. Dewick. We would use V orb equals the square root of big G big M over R orb. I'm going to skip this. We could find it. However, if I gave this question to you without part A, if I just gave you the period, which I will, and I said find the velocity, you'll have to find the radius first, I think. Okay. So let's put that equation in here. What was it? R orb was equal to the cube root of, was it G M T squared over 4? Is that what it was? I've never bothered memorizing it because I can just derive it with, be careful with your cross multiplying, but it's really math 8. All we're doing is cross multiplying. Oh, I guess cube root is technically, what, math 10? Fair enough. You can add that one to your blue sheet if you really want to. Again, I'd encourage you to get comfy with the derivation. Pause for a second, put your pencils down.